Hi, I'm David Zuckerman. I'm a professor of computer science at the University of Texas at Austin. That's the UT Tower behind me. I got interested in theoretical computer science because it's a great way to apply interesting mathematics to compelling questions. So the theory of computing relates to many disciplines, and there are many simply stated challenging problems. My focus is on randomness and computing, mostly pseudo-randomness, and you'll get a flavor of that today. So let me share my screen. And let me start from the beginning. So again, I'm going to discuss randomness and computing. Maybe the most basic thing in randomness is random sampling. So just think about flipping a coin. Let's say we flip a fair coin 1,000 times. Well, the number of heads will be 500 plus or minus 35 with 95% certainty. And if you do it with n coins, you'll get n over 2 heads plus or minus square root n heads with 95% certainty. So this converges to fraction 1/2 very quickly. And this is useful not just in computer science, but more generally. So in polling, for example, there was a recent Gallup poll asking people if they want to abolish the Electoral College. And here they just asked 1,000 people, and with 95% confidence, they can get the right answer, plus or minus 4%. So the United States has a huge population, 300 million or more, but you can choose a sample size independent of the population. So in fact, it wouldn't matter if the US had a population of 300 trillion, still a sample size of just 1,000 would suffice to get high confidence of the right answer to within a small margin of error. And this idea is useful in computer science. So for example, suppose we want to calculate the area of some region. And this is a very complicated region that we can't get our hands on. We don't know how to integrate anything here. All we can do is tell whether or not a point is in the region or not. So let's say that's the case. And we also know that this region is contained inside some square, say. Well, we can choose many random points in the square, and we can compute the fraction r of these random points that lie in the region. And we can take as our area estimate of the region r times the area of the square. This is very natural. And with high probability, it will give a good estimate. So this idea is used throughout computer science. There are much more sophisticated random sampling techniques that are used to approximate various quantities. So if you want to approximate the volume of a region, sometimes the situation is not as simple as I said. You can use more complicated techniques to estimate the volume of a region. You can also use it to estimate an integral, which is similar to a volume. Or you can use it to approximate the number of solutions to an equation. It's also useful in load balancing. So here you may have a computer that has many cores and jobs come in. How do you distribute jobs to the cores? Well, a natural thing is actually just to distribute them randomly. And this balances out the load pretty well. In practice, randomness is used a lot in Monte Carlo simulations. So these are simulations of complex systems that are done on the computer. So for example, the economy, or the weather, or molecular interactions can be simulated using sophisticated models. And these models often have random components. So these random components can model actual randomness, for example, coming from quantum mechanics, or just complex phenomena. It's sometimes convenient just to model them as randomness. Randomness is really useful in cryptography. So if you want to buy something online, you're using randomness. And it's really essential for secure communication. Because if the secret key is not random, then the eavesdropper could learn it. So it's crucial that that cryptography uses high quality randomness. So outline of this video, I want to discuss randomized algorithms with an example. Then I'll discuss complexity classes RP and BPP. And then we'll discuss the question of whether BPP equals P. And this will lead to a discussion of pseudorandom generators. In this first video, I'm just going to talk about randomized algorithms, and I'll introduce RP. Just as a quick refresher, probably all of you know this, but if I say a random bit, I just mean that X takes on the values 0 or 1 with probability 1/2. And if I say a random integer from 1 to 100, I mean that for all I, the probability that Y equals I is 1 over 100. And if I talk about independent random bits, I mean that for any I conditioned on all the other xj, xi is still a random bit. Or equivalently, if you take any 100-bit string, the probability that x1 through x100 equals this fixed 100-bit string is exactly 1 over 2 to the 100. Okay, so now let's look at a randomized algorithm as an example. So here we have this example. Does 12 to the 2,000,001 plus 7 to the 442 equal this right-hand side? So this is, these are pretty big numbers. The natural algorithm is to multiply it out and add. The problem with that is that it's very inefficient. You need to store 2 million digit numbers. These are quite big and not easily stored in a computer. And in general, deciding whether a to the b plus c to the d equals e to the f plus g, if you just do it naively in this way, this is going to take exponential space and hence exponential time. So this is not a good way to do that. Is there a better way? Well, it's natural. Let's start out looking at this specific example. If you look carefully, you can actually see that these are not equal without doing any complex calculation. Why? Because the left-hand side is odd. It's an even number plus an odd number. And the right-hand side is even. It's an odd number plus an odd number. Well, is that just a cheap trick? What if both sides are even or both sides are odd? What can you say then? Well, the insight is that odd or even is the remainder modulo 2. But why is 2 so special? What about looking mod other numbers? So this hints at the randomized algorithm. To test if the two sides are equal, we'll just pick a random number between 2 and some pre-specified bound. Don't worry too much exactly what this is, but note that it's a reasonable number. It's logarithmic in the quantities we're interested in. So it's not too big. So in our example, it's less than 15 million. You might think, well, oh, 15 million sounds big. But remember, 15 million is just 8 digits. It's easily stored in a computer. So it's really not that big. So we'll pick this random number and we'll compute the remainder modulo r. And we can do this efficiently. How? Because we do have to, it is a little tricky in that we have to raise numbers to very large powers, but we can do that by repeated squaring. So if we have to raise a number a to 2 to the k, we'll just square the result k times. And this requires just k multiplications instead of 2 to the k. And this is how we're going to get polynomial time. We'll only keep track of the remainder modulo r. So for example, if we want to compute 7 to the 5th mod 41, we write 7 to the 5th as 7 squared times 7. So this is 49 squared times 7. 49 is congruent to 8 mod 41. So we get, this is congruent to 8 squared times 7. 8 squared is 64, which is congruent to 23 mod 41. And then we just do 23 times 7, which works out to 38 mod 41. Okay, now, of course, if the two sides of this equation are equal, then the remainder mod R of both sides are equal. And the interesting thing to show is that if the two sides are not equal, then the remainder mod R is not equal with probability at least a half or even bigger than half. So this error probability, and note that we can improve the error probability by repeating. So suppose we start with error 1/2. If we repeat it k times, the error becomes 2 to the minus k. Because in order for an error to occur in this whole process repeated k times, an error has to occur in each of the k runs. And the probability of an error occurring in each of the k runs is at most 1/2 to the k. So let me sketch this lemma. So we let m be the difference of the two sides. So we want to see if a to the b plus c to the d equals e to the f plus g. We'll let m denote the difference in absolute value. And now we want to test if m equals 0. Well, again, m equals 0 is, there's nothing really to prove. If m equals 0, the two sides are equal. The remainder mod R is equal. The interesting case is if m doesn't equal 0, we want to show that the remainder mod R on both sides is not equal with decent probability. And that's equivalent to showing that m mod R is not 0. So the key claim is that there aren't too many primes that divide m. In fact, there are most log m primes that divide m. Why is that? Well, if p and q are different primes, both dividing m, then their product divides m. More generally, if there are distinct primes dividing m, then their product must divide m, which means if m is bigger than 0, that means that m is at least the product of all these primes. And each prime is at least 2, so this is actually at least 2 to the r. And that's it, we're done. We've shown that m is at least 2 to the r. Taking the log base 2 of both sides says that r is in most log base 2 of m, and that's what we wanted to show. This notation LG stands for log base 2. Okay, so let's analyze a slightly different algorithm. In fact, we could use this algorithm instead. It was just simpler to state the other algorithm. Here we'll choose a random prime among the first two R primes. Call this random prime P, and we'll test if P divides M. So the probability that P will divide M, well, there are most R primes that divide M, and we're picking P among two R primes. So this probability is at most 1/2. And note that P divides M is equivalent to A to the B plus C to the D, congruent to E to the F plus G mod P. Okay, so this is exactly so this corresponds to the algorithm that we were looking at before, except now we're picking a random prime instead of a random number among the first so many numbers. And so this can all be done in randomized polynomial time. Okay, so that's a sketch of the algorithm. And randomized algorithms are useful in many different areas. So we've just looked at algebra and number theory. I just showed you this algorithm for equality testing. It's also useful in testing whether a number is prime. I'll give you a flavor of that in the next video. It's useful in factoring polynomials for polynomial identity testing. It's useful in graph theory for min-cut, shortest paths, minimum spanning trees. As I mentioned earlier, it's very helpful in approximate counting. You can compute the volume or approximate the volume in this method. You can approximate integrals. You can approximate the number of solutions to equations, the number of satisfying assignments, the permanent. You can also approximate optimization algorithms where you want to approximately optimize some quantity. So as you may know, stochastic gradient descent is a randomized algorithm that's extraordinarily useful in machine learning. most of the advances that you see coming out in artificial intelligence trace back to the effectiveness of stochastic gradient descent. It's also useful in combinatorial optimization algorithms such as maxcut or maxsat. And there are many more that I don't have time to describe. So these randomized algorithms are often much faster and are simpler than known deterministic counterparts. So let's try to view them in a complexity theoretic framework. So let's discuss randomized polynomial time. We say that a language L is an RP for randomized polynomial time if and only if there's a randomized algorithm. I'm writing it as there exists a probabilistic polynomial time Turing machine, which I'll define in a minute. So if and only if there exists a probabilistic polynomial time Turing machine M, such that if a string is in the language, the probability that M accepts it is at least a half. And if the string is not in the language, M will never accept it. It accepts it with probability 0. So a probabilistic Turing machine is just a Turing machine that can access random bits. So just think of it as a randomized algorithm. It's convenient not to think of Turing machines for now. You've seen earlier that Turing machines are equivalent to maybe easier models to think about, like the RAM model. But you can think about your favorite model and think about a randomized algorithm in that model. So for example, unequal is an RP, where unequal is a set of 7 tuples such that a to the b plus c to the d doesn't equal e to the f plus g. Because remember, if we take this mod a random prime with probability at least 1/2, the two sides are different. So we can output unequal. And if the two sides start out being equal, if we take it mod a random prime, they'll still be equal. We'll never say they're unequal. Okay, so it's unequal that's in RP. This is not a symmetric definition. So you need to check. It's not equal that's in RP, but unequal. And RP, of course, contains the class P, because if M were a deterministic algorithm deciding L, well, then M would accept with probability 1 if W is in L, and with probability 0 if W is not in L. So it would satisfy these conditions here. It's also in NP. Why is that? Well, certificate that W is in the language is just some random string that causes M to accept. So in our example, a certificate is some prime that gives a to the b plus c to the d mod p different than e to the f plus g mod p. In fact, in that original example, p was just 2, and I showed you that the left side was odd and the right side was even. So that was sort of an example of an NP certificate. So in fact, you could think of RP as NP where there are lots of witnesses or lots of certificates, right? With probability 1/2, if you just pick a possible certificate at random, with probability 1/2, it will be a valid certificate. So that's what RP is. Another way of thinking about it is that NP corresponds to, instead of at least a 1/2 here, greater than 0 here. So for example, if language L was sat, if we just picked a random assignment, with if it's satisfiable with probability greater than 0, this will be a satisfying assignment. But if it's unsatisfiable, it will be a satisfying assignment with probability equal to 0. Okay, so it's very similar to, it's very related to NP. Okay, so that's the end of this first video. In summary, we've seen an example randomized algorithm that works very well. We don't know how to solve it deterministically, and we can capture randomized algorithms by this complexity class RP. Okay, so we'll continue here next time. Okay, last video we introduced randomized algorithms. We saw an example of unequal. We gave a randomized algorithm based on picking a random prime and computing both sides mod this random prime. And then we introduced the complexity class RP, standing for randomized polynomial time. And we saw that RP is contained in NP and it contains P. And today we're going to explore this class further. We're going to see primality testing, and we're going to see a generalization of RP. Testing whether a number is prime has fascinated mathematicians for some 2,000 years. So the naive algorithm to test if a number is prime is trial division. Test if n is divisible by 2, 3, 4, etc., up to square root n. Or you could just look at try to divide by the primes up to square root n. It won't really matter much. This takes time about square root n times polylog n. So some people, when they see this, they think that this is a polynomial time algorithm, but it's not, because the input length is just log base 2 of n. Right? The number big N can be expressed with just log base 2 of n bits. So let's call that little n. And then this is exponential in little n. Now, composites is in NP. A certificate is a non-trivial factor. So the randomized algorithm is not going to be just try to pick a factor at random. That's not going to work because there aren't too many factors. So we'll have to do something quite different. But nevertheless, we'll be able to show that composites is an RP. Now, in fact, the certificate cannot be a factor because factoring is believed to be hard. So we'll actually be able to show the number is composite without exhibiting a factor. And how can we do this? Well, we'll appeal to something called Fermat's little theorem, which says that if P is prime and P does not divide A, then A to the P minus 1 is congruent to 1 mod P. So proof that 6 is composite is that 5 to the 6 minus 1 is not congruent to 1 mod 6. Now, this is a silly way to show that 6 is composite, but for larger values of 6 or whatever number you want to test, it turns out to be a good method. So here's a wishful converse to Fermat's little theorem. Suppose that M is composite. Then for at least half of the A's between 1 and M minus 1, A to the M minus 1 is not congruent to 1 mod M. Right? If M is prime, this holds for all A. But if M is composite, we hope that it holds for, if M is prime, it's congruent to 1 for all A. If M is composite, we hope that it's congruent to 1 for at most half A. And if true, we could just test this for a random A between 1 and M minus 1. And from group theory, we might hope that this holds because the size of a proper subgroup is in most the size of the group over 2. If you don't know group theory, just ignore this sentence. But this is false for M equals 561. In fact, there's a whole group of numbers called Carmichael numbers for which this doesn't hold. But Solovay and Strawson proved something that's just as good for our purpose, pretty much. They showed that if M is composite, then for at least half of the A between 1 and M minus 1, if we raise A to the M minus 1 over 2, we don't get something called the Jacobi symbol of A mod M, of A and M modulo M. For comparison, if P is prime, then for all A, this holds. And here again, this is the Jacobi symbol. It's not too important what it is, just that it's polynomial time computable. So if we choose A randomly, we can distinguish the case whether M is prime, in which case this equality always holds, versus when M is composite, in which case this is going to be unequal for at least half of the values. So if we choose a random A, this shows that composites is in RP. So their certificate is when a to the m-1/2 is not congruent to j of am, right? Because if it is congruent, that it could be prime or composite. Okay, so that's a rough idea. Okay, so this class RP is extremely useful. It captures things like composites, and we saw a toy example earlier, but it's not necessarily the most general form of a randomized algorithm. An RP algorithm will never say yes when the answer is no. But what if we want to capture randomized algorithms that might err in both directions? So the complexity class BPP allows both types of error. BPP stands for bounded error probabilistic polynomial time. It's kind of a weird name, but that's the name. So we say that a language L is in BPP if and only if there's a probabilistic polynomial time Turing machine M, such that if W is in the language, the probability M accepts W is at least 2/3. Whereas if W is not in the language, the probability of acceptance is at most 1/3. And like in RP, we can reduce the error via repetition, but this time it's not so obvious. We will see a proof later, but it's not obvious, but you can accept it for now. Now, RP is contained in BPP. Right, we saw an RP algorithm accepts with probability at least 1/2. If we repeat it twice, it accepts with probability at least 3/4. But it's unclear if BPP is contained in NP. There's no obvious certificate here. So even though BPP may not be contained in NP, BPP is contained in P space. And the proof of this is as follows. Suppose L is a language decided by some BPP machine M that uses R random bits. Since M runs in polynomial time, R must be polynomial in the input length N. So it's convenient to think of M as having two inputs, the real input W and the random bits Y that it uses. So Y being an R bit string, because we said it uses R random bits. So here's a P space algorithm for the language L. On input W, we're going to run this machine MW on MWY 2 to the R times, once for each different R bit string Y. Right? We can't choose this Y randomly, which we'd like to do because we don't have random bits now, but we'll just cycle over all possible choices of Y. There are 2 to the R of them. And we'll reuse space between runs, and we'll just keep a track of the total count. We'll call it count, which is the number of Y causing acceptance. And we'll accept if the count is bigger than 2 to the R minus 1. So this corresponds to accepting if and only if the probability M accepts is greater than 1/2. Since the probability that M accepts is exactly equal to the count divided by 2 to the R, that is the number of accepting strings divided by the total number of strings. So this is correct almost by definition, and it runs in polynomial space because we reuse space between runs, and we're just keeping track of this count that stays, but that we need to keep track of throughout, but this is easily stored using R bits. So as a corollary, since BPP is contained in P space and P space is contained in exponential time, BPP is contained in exponential time. Okay, so BPP is not too powerful. Now let's see error reduction for BPP. So we can reduce the error to be exponentially small. And we do it in the natural way. We'll repeat the algorithm a bunch of times and take the majority vote. We'll break ties arbitrarily, that won't matter. it's convenient for the proof to say we'll run it 2k times rather than k. You'll see why in a minute. So let's suppose the original probability of error is p, which is at most 1/3. Right, so this could be, we have a yes instance and the probability that the algorithm outputs no is at most 1/3, or vice versa. We have a no instance, the probability that it outputs yes is at most 1/3. The definition of BPP is symmetric in this way. So the probability that I of the 2k runs, right, we're running it 2k times, the probability that I of the 2k runs give an error is exactly the number of possible ways to pick which of the I runs give an error. That is 2k choose I, times the probability that these I choices give an error, that's p to the I, times the probability that the other choices do not give an error, that's 1 minus p to the 2k minus I. Now, the biggest error for majority occurs when p equals 1/3, so it's convenient to just think of p equals 1/3. Okay, so now let's use this, and we could see that the probability that the majority of 2k runs error is at most the following. So bear with me, this is a lot of equations. But this is at most, well, we'll sum up I equals k to 2k. So this is the probability, we're interested in the probability of I errors. So we'll get an error if the number of errors I is between k and 2k. And we've already seen that the probability that an error occurs is 2k choose I times 1/3 to the I times 2/3 to the 2k minus I. Well, I claim that we can upper bound this quantity as follows, right? 1/3 to the I, 2/3 to the 2k minus I. Well, this is largest when I equals k, right? Because if as I gets larger, we have more 1/3s and fewer 2/3s. So this product is largest when I equals k. That's what this bottom line says. 1/3 to the I, 2/3 to the 2k minus I is at most 1/3 to the k, 2/3 to the k. So that's where we get this second term here. And the first term here, we can now pull out the sum of all these binomial coefficients. Well, the sum of these binomial coefficients is at most the sum of all the binomial coefficients. And that's exactly equal to 2 to the 2k. So that tells us that this whole sum is at most 2 to the 2k times 1/3 to the k times 2/3 to the k, which is 8, which just multiplying gives 8/9 to the k. So this is exponentially small in k. Okay, and that's the whole proof. Okay, there's something called Chernoff bounds, which if you believe Chernoff bounds, they give you the result as a corollary. So these are more general tail bounds. There are various forms. Let me just state one of them. We'll let y be the sum of xi, where xi are random variables taking values in the range 0, 1, and the xi are independent random variables. And let mu equal the expectation of y, which by linearity of expectation is the sum of the expectation of xi. Then the probability that y differs from its expectation by at least epsilon mu is at most 2e to the minus some constant times mu, where this constant depends only on epsilon. Okay, so the error, so the chance that you deviate from your expectation by some constant fraction of the expectation is exponentially small in that constant, is exponentially small in the expectation. So in our setting, we could set xi equal to 1 if there's an error in the ith run and 0 otherwise. So the expectation of xi is just the probability of an error, which is p, which we said was at most 1/3. So the expectation of y is equal to 2kp, which is at most 2k over 3. And we can take epsilon equal to 1/2 because, oops. We could take epsilon equal to 1/2 because half of 2k over 3 is k over 3. And there will only be an error if y differs from its expectation by k over 3. And that corresponds to epsilon equal to 1/2. So this tells us that the probability is exponentially small in 2k over 3, which is exponentially small in k. Okay, so summarizing, comparing RP and BPP, RP is one-sided error, and P is contained in RP, which is contained in NP. BPP is two-sided error, and BPP contains RP that's contained in P space, and hence exponential time. And the error can be made exponentially small. So it's natural to ask, is RP or BPP closer to P or closer to exponential time? And this is what we'll explore in the next video. Okay. All right, so this is a fundamental question that we'll look at closer next time. Okay, so last class we discussed RP and BPP, and we saw two examples of randomized algorithms. So RP is one-sided error, and it's sandwiched between P and NP. BPP is two-sided error, and it's sandwiched between RP and P space. The error can be made exponentially small. And we concluded by asking whether RP and BPP are closer to P or to exponential time. And this can be motivated from practical considerations. That is as follows. So randomness is wonderful. We have these great randomized algorithms, but computers typically don't have access to truly random bits. For example, they could try using the exact time of a clock. So for example, the last 3 digits may give a sort of random number. But of course, the program may check the clock in regular intervals. So this could be terrible because then all the random numbers differ by the same amount. You could have 2 clocks, and this is called clock drift. But it's unclear how much the clock will drift. You could use other operating system variables, but again, it's unclear how random these are. So it's natural to ask, is randomness necessary? It is essential for cryptography because if the secret key is not random, the eavesdropper could learn it. But it's unclear for algorithms. For example, I showed you the randomized algorithm for composites. That was done in the late 70s. And for a long time, we didn't know a deterministic polynomial time algorithm for composites, or equivalently for primality. But in 2004, 3 researchers gave a polynomial time algorithm for primes and hence composites. So primes is actually in P. So could it be that every problem in RP is contained in P? Or could it even be that BPP equals P? Well, let's explore that question. A key to exploring this question is the notion of a pseudorandom generator. A pseudorandom generator is a deterministic algorithm that takes as input a short random string and outputs a long string that's hopefully random enough. So here, I didn't even use any randomness to generate this string. I just took the digits of pi after the decimal point. Is this random enough? What does random enough even mean? So for a long time, people used ad hoc definitions of random enough, whether it passed a few statistical tests. But there's a modern approach. I say modern, but this is really from the 80s. Since I'm old, I can call that modern. And here the approach is to require a pseudorandom generator to fool all efficient algorithms. What does that mean? It means you have an algorithm that it has an input and it has some behavior when it's fed a random string. We want the behavior to be approximately the same when it's fed a pseudo-random string. Here by behavior, we mean the probability that the algorithm accepts if it's just an algorithm that outputs yes or no. And efficient, we typically want polynomial time. So an approach to BPP is as follows. Here's a conjecture that says there is a polynomial time pseudorandom generator G that outputs R bits using a seed of just order log R bits that fools algorithms running in polynomial time with error, say 0.1. And this is known to be true under plausible lower bounds, under an assumption about lower bounds. So you assume believable lower bounds, and then you can prove this conjecture. However, lower bounds are notoriously hard to prove, so we don't expect to prove these in the near future. But we can prove that this conjecture implies BPP equals P. Why is that? Well, we do the same argument that we use to show that BPP is in P space, but instead of R bit strings, we use the order log R bit seeds. So we cycle over all order log R bit seeds. and we run M of W, and we apply the pseudorandom generator to the seed Y. Okay, so now we don't have so many possibilities for G of Y. We only need to run M a total of 2 to the order log R, which is polynomial in R, which is polynomial in N times. So we only need to run M a polynomial number of times and keep track of the count. And this can all be done in polynomial time. And the correctness follows because the original, we started out being correct with probability 2/3. The pseudorandom generator only introduces an error 0.1. So our new error after taking the pseudorandom generator into account is still the new error is at most 1/3 plus 0.1, which is at most 44%. Okay, so the new algorithm errs with probability at most 0.44. So in particular, the majority will be correct. This computes the actual majority, right? We count how many of these G of Y's cause acceptance, and we just take a majority vote. So as long as 44% cause an error, the majority will be correct. And this is a deterministic algorithm that will always be correct. Okay, so in conclusion, we've seen many powerful randomized algorithms. We saw unequal composites, and there's a whole bunch of others that we don't have time to discuss. There are whole courses on randomized algorithms. And they decide languages in the complexity classes RP and BPP. And we can make the error exponentially small just by repeating many times. RP is sandwiched between P and NP, and BPP is sandwiched between RP and P space. And there's evidence that BPP equals P, and which implies RP equals P. But we're very far from proving this unconditionally. Okay, so I hope this gives you a flavor of the use of randomness in computing. It's very powerful on the one hand, but on the other hand, we actually believe that maybe we can eliminate the need for randomness, at least up to polynomial factors. I mean, randomness is still useful, even for primality testing. So in practice, people still use randomized algorithms, even though we have this deterministic polynomial time algorithm. Okay, so I hope this inspires you to learn more about it. All right, thank you.